All of the relationships that you have come to understand about triangles can be used to prove certain properties about the special segments and special angles in circles. Yesterday, we whipped up this circle for problem number 10-5. Let's see if we can get back to the given information. We were told that we had a chord on a circle called WX with a center called Z, and that chord was 8 units. We were also told that the radius of circle Z was 5 units long. So adding that information to the diagram, and as always, this needs to be your first step. Draw what you know. Adding that information to the diagram gives you a really interesting problem. How far from the center is the chord? Well, I don't have any idea unless I keep playing around with the information I'm given. Oh, now I see that I have a perpendicular bisector that I created with the perpendicular line tool through the center of WX. Well, I'm now seeing that W to the bisector has to be 4. I know it's perpendicular. I have a radii of 5 that is immediately screaming out 3, 4, 5 triangle. So whipping up a diagram is the first step. If you're very familiar with GeoGebra, it's a really good calculator. So open it up as you work on these problems. We just use the circle tool to create a circle, and I'm just going to create a diagram that's similar to 10-15A. And I'm going to change the labels using the object property. In BASIC, you're allowed to give the figure any name you want. So I'm going to right click on each of these and change the labels to match the diagram given in 10-15. Now the important piece of each of these inscribed angles is that they're created with the same intercepted arc. So let's add an angle from K through G to J, the same intercepted arc. And then we see that the measures are the same. And then let's add the segments to highlight these angles. And let's do that one more time. K through F to J, and add the segments. I wonder if there's a way to create the arc from J to K and change its color. Looks like I can use the circular arc tool with select a center and 2 points. So I need to put my center back on. Doesn't look like it was A, perhaps it was F or G or P. There we go. Select a center and 2 points. So let's change the color of this arc so that we can clearly see the intercepted arc. Ooh, that's kind of cool. It gave me the segment. That's not exactly what I wanted, but I like it. I'm just going to make it a little less thick. Interesting. It's still giving me the segment, and I'm not sure exactly why. But that's not a bad visual to have. Each of these angles, let's change the color so they're pink. And I'll change the opacity to match as well. I've captured an image of the inscribed angle. I want to see if I can insert it here. And let's see what kind of playing around with it I can do. I don't want to change the size, but I do want to, actually I can change the size, right? Because that's not going to change the size of the angle. Okay, this is good news. So if I can capture this angle, this is just an image, and I can place it over each of these. I wonder if I can use this captured image to talk about the relationship between the inscribed angle and the central angle created at the same intercepted arc. Let's try that. So here's my central angle. Is it 24 7/100? I'm going to change the color of these radii and then show you that the angle created at the same endpoints of the arc, the central angle, has a measure of 48 1400. And let's just change the rounding to 0 places. And the only one that didn't change is the one I've taken an image of. That makes sense. So the inscribed angle measures 24, but the central angle measure is 48. What is the relationship there? Can I place these in such a way that we can see the relationship between the inscribed angle and the central angle? So 24 is to 48, how? Let's go ahead and put this image in again. Is one twice the other? And will that always be true? If we line this up on T and I change this, let's make it parallel first and then slide it over. It is true that the measure of, oops, I'm moving my circle. That's not a bad idea either. That the measure of the inscribed angle is half the measure of the central angle. It's reliable, and it's a calculation we can use to make judgments about other circles, which we're going to do together in 1016. So open up the text to 10-16 and go ahead and draw those 6 circles. You must be willing to draw the circles. Please stop this tape, do that now, and we're going to finish these together. In 10-16A, we're given an arc measure of 118 degrees. We know that the arc measure corresponds to the central angle, so let's put a center in the circle. And let's construct the central angle intercepted at the same endpoints. Oh, wait a second. How do I do that? Segments. So we know if the arc measure is 118 degrees, we know that the measure of angle, the central angle at the center, has to be 118 degrees. I have an R sub 1 in the center, so Q sub 1 R sub 1 W is an angle with a measure of 118 because it corresponds to my given arc measure. Therefore, the angle at X down here has half the value. Where'd my text box with X go? Has half the value of the central angle. So 118 divided by 2 is 59 degrees. In A, X equals 59 degrees. Because the measure of an inscribed angle is half the measure of the corresponding central angle measure. So you're going to find a way to use the information in the text, in the message, in the math notes, message and meetings, more circle vocabulary. You're going to find a way to develop a strategy for learning those relationships and that vocabulary. In B, we're told that the measure of the inscribed angle is 41, and we're asked the measure of X. Well, X is the measure of the arc, which corresponds to the measure of the central angle, which is double the measure of the inscribed angle. If the inscribed angle is 41, then the central angle must be 82, then the arc measure must be 82, based on the relationships outlined in the methods and meanings math notes box for more circle vocabulary. As you practice these, you're concentrating on developing a way to remember these relationships. 41, 82, 82. In C, we have a right triangle inscribed in a semicircle. The really interesting thing is that when you inscribe an angle with endpoints at the diameter, it doesn't matter where I drag the vertex, this triangle created here remains a 90-degree angle, a 90-degree triangle. That's a pretty cool result, actually. Pretty easy to see here. When we create a perpendicular bisector through the center of the circle, and we match the vertex up on that perpendicular bisector, we now have congruent triangles. Here's our 45, 45, 90. But even as we drag W, the vertex, away, this triangle remains a right triangle because it is inscribed within an arc that has endpoints on the diameter. It's pretty cool. We're asked to find values for X, Y, and Z in this case, and we're told this is 78 degrees. We know the relationships. If this is 78, this is 156. Therefore, Y, the measure of the arc, is 156 because it has the same measure as the central angle.